Welcome to Biomaterials. What are we going to talk about today? Today we're going to talk about polymer synthesis. And understanding, at least in a qualitative way, polymer synthesis is important because that allows us to understand how certain polymers are made and the limitations and benefits that we can take by sort of tweaking the parameters that go into polymer synthesis. And it also helps us identify, which types of polymers are made in certain ways, so we can sort of understand, how they might be generated either by our bodies or by generated in mechanical in industrial and manufacturing processes. And by sort of understanding how polymers are made, we can understand what limitations are in terms of our ability to make polymers, and also how the limitations in terms of our ability to make these polymers impact their use. But we're not going to go into all of those details today. Today we're going to sort of just generally talk about the types of polymerization. It turns out there are three types. Well, the three types are condensation reactions. So condensation. The second type is radical. And the third type is ring opening. And basically each of these three types of polymerizations, the monomers all look different from one another. They each have sort of distinct molecular motifs that sort of give away what type of polymerization reaction what types of polymerization reaction might give rise to a bunch of monomers joining together to become polymers. And then sort of after we discuss, what type of polymerization reaction goes into making each of these, we'll then talk about sort of how the chains grow, how chains form or grow. Sort of what do they look like as they're forming? How do monomers join the chain? All this stuff, and it basically turns out there's sort of two main ways that chains can grow. One is called step growth, and the other is called chain growth. So let's get started with condensation polymerization first. So condensation polymerization comes about from the idea that monomers are condensed in when they're reacting with one another to form bonds, and this condensation comes. For most condensation reactions, basically the condensation comes off, so monomers join one another. So monomers join, and when they join, they typically release some small molecule as a byproduct of the reaction. I'll use RxN to abbreviate reaction in this case. So if you dust off your first year or high school biology notes, you'll know that one of the favorite condensation reactions in bioengineering is an example of this is amino acids. And I'm never going to expect you to memorize, all of the different types of reactions that can form condensation things are here. But, if you are going to remember one in the context of this class, if you remember amino acids, basically there's some sort of central part of the molecule. And on one side of the amino acid is a carboxylic acid group, which is COOH. Right, so this is what we call a carboxylic acid. And then on the other side of an amino acid is what we call an amine group. So it's an NH, an NH2, and then amino acids join one another to become polypeptides, or i.e. proteins, by the amine group on one side reacting with the carboxylic acid group on the other side to form a bond, right? So for example, we might have one amino acid right here and another amino acid right here, and the NH2 and the COOH. These react with one another. These react with one another to create this bond. So we get a CO and an NH right here, and then and of course, if you do your bookkeeping and compare all of the atoms that were in these two molecules and all of the atoms that were in here, when this reaction happens, you'll realize that we're missing one H2O that went into this bond. So basically, condensation comes from the idea that you actually have more molecular weight if you summed up all of the monomers than you would have for the molecular weight of the polymer that they ended up forming. So in a sense, it's condensed, and when it condenses together, it kicks off a water. There are other types of condensation reactions. For example, some that kick out hydrochloric acid and some that kick out other molecules. But this is just an example of one type of thing that forms. So when we think about condensation reaction and the way that polymers grow via condensation reactions, one of my favorite analogies is with Lego blocks, or I guess this is Duplo. So we can think of each amino acid as a block, where basically there are holes for the pegs to go in, and there are pegs on the other side. So we can think of maybe the amine groups like the holes and the carboxylic acid groups like the pegs. So if I have two amino acids, I can join them together like this. And this for example would be the peptide bond or the amide bond that they would form together. And then polymerization can happen again and again, where another amino acid could join this side of this chain. And we could sort of further the size of the chain. Of course, no water is actually kicked out for these Lego blocks, but you could imagine there's some a water molecule here that sort of gets kicked out when they form this bond. So this for example, this is a mechanism by which some types of polymers, natural ones like proteins, but also some artificial ones like nylon, form via condensation reactions. Let's now make things a little more radical by talking about radical polymerization. I'm going to talk in much more detail about radical polymerization from sort of a more quantitative or a more analytical standpoint later. Here we're just going to mostly talk about qualitatively what's going on. But radical polymerization, basically the key with radical polymerization is you break a carbon-carbon double bond. You break a carbon-carbon double bond to have a monomer join a chain. So when we have these carbon-carbon double bonds to have a monomer join a chain, one example of a type of polymer that's formed via radical polymerization is polyethylene. So polyethylene, the monomer, again, remember the monomer is ethylene. So ethylene is carbon-carbon. There's a double bond between them, and the remaining slots on the carbon are taken up by hydrogens. Of course, if we wanted to use the simplified organic chemistry notation, ethylene would just look like this, right? Because you would assume there are carbons at the endpoints. There's a double bond here, and that any of the unoccupied spots on the carbons are occupied by hydrogens. So that's our simplified thing. But just so you can visualize, all of the slots for what's happening with the carbon that's here. And if you remember, these double bonds are basically these double bonds here. Take a moment now, pause and ponder. How many electrons are in this double bond? So take a moment now, pause and ponder. How many electrons make up this double bond? Well, if you remember, if you dust off your high school chemistry, a single bond is equal to 2 electrons, right? So remember, two electrons pair together. Atoms sort of hate to have unpaired electrons in their outer orbitals. So a single bond is basically two atoms that would have had unpaired electrons hanging out next to one another, where they each contribute 1 electron to the bond, and those bonds are shared. If you have a double bond, each electron, or each atom comes with sort of 2 electrons to share. So double bonds are actually made of 4 electrons. So double bonds are 4 electrons. So what implication does that have for radical polymerization? Basically, what happens when we're doing a radical polymerization is there's a carbon-carbon double bond, and 2 of the electrons that participate in this double bond get broken up and put elsewhere in the molecule, and that helps us with the chain growth. So if you remember polyethylene, so ethylene looks like this. It's a gas at standard temperature and pressure. Polyethylene, if you remember, is just this very long hydrocarbon chain. So how do we go from having double bonds in the monomer to having just a polymer that's composed entirely of single bonds? Well, let's take a look here. So imagine I have a chain of polyethylene, but in my very last carbon in this chain, I have a hydrogen and a hydrogen. And we'll talk about details in the next lecture, but imagine for this carbon, I have an unpaired electron. I have an unpaired electron here. Well, this carbon, this is a very unstable situation for this carbon to be in, because if you went back to high school chemistry and drew some electron diagram around some atom, and you had an unpaired electron in there, you probably would have failed the quiz, right? Because they'd be like, never, we never have unpaired electrons. Well, we actually do, and an unpaired electron has a special name in chemistry. It's called a radical. So another word for an unpaired electron is a radical. So what happens to this radical in polymerization? Well, there's an ethylene molecule comes by and interacts with this unpaired electron. So we have, let's say, a carbon, and there's a double bond here. Now, I'm going to, instead of imagining this double bond, sketching it right here, if you remember, there are 4 electrons in this double bond here. I'm going to imagine 2 of these electrons as being a single bond, And I'm going to pretend that the other 2 electrons that participate in this double bond, I'm going to sort of draw them as if they were not joined together to form a second bond, but rather sort of acting separately. So this is the other 2 electrons. Well, basically what happens is, these 2, if you, just by themselves, these 2 electrons and these 2 electrons are very happy participating in this double bond, but along comes this radical here, and it does the unthinkable. It steals one of the electrons from this double bond over to forming a single bond between here. So basically what happens is these electrons form a new single bond. And what does that do? Well, interestingly enough, I should draw the other hydrogens that were around. The other hydrogens that were around here. What does that do? That basically, these 2 electrons coming together form a new single bond between these carbons that were originally separate. This single bond remains as a single bond between these 2 carbons here. And what was this unpaired, what was a paired electron, now this becomes an unpaired electron out here. Right, so this guy is now unpaired out here. Let me just fill in the hydrogens. And basically what that happens, well, now if you imagine, if we kind of go back to where we were here, we started off with a carbon that had an unpaired electron. We ended off with a carbon that had an unpaired electron. So this guy right here is now ready to add another ethylene monomer. So what happens, right? Basically, we started off with an unpaired electron and a monomer. The monomer joined up, and through that monomer joining up, that then created basically another unpaired electron that's ready to join up with the next one. So what does this look like in practice? Well, it turns out you need to start off with some kind of initiator. So imagine that all of these blue things are ethylene monomers. We have some initiator, and so initially these ethylene molecules, these are all like this. Pretend that they can't really stick to one another when they're just by themselves. But some initiator comes along, starts a chain growing, and then basically once this monomer has joined this chain, that readies up this end. You can imagine there's an unpaired electron on this end right here. That snags another ethylene molecule and pushes over an unpaired electron to be right here, and then this process can just continue with the unpaired electron continually getting shifted to the end, and more monomers joining the chain until we have chains of polyethylene that are so long that the molecular weight is in the tens or hundreds of thousands, something like that, of grams per mole. So this is basically radical polymerization. So what's the key thing? How might you identify how might you identify a molecule that's made via radical polymerization? So the key features here are noticing that the backbone of the polymer is entirely made of carbon single bonds, right? Whereas in contrast to condensation, if you look, there might be some carbon single bonds here, but there's a carbon nitrogen kind of back to carbon or back to other stuff over here, right? So in condensation, we notice that there are sort of these other types of molecular motifs that sort of interrupt the chain. In radical polymerization, basically you have this carbon-carbon double bond, and that ends up with a chain of purely carbon-carbon bonds along it. It turns out polyethylene isn't the only molecule made via radical polymerization. Some other examples of radical polymerization. So some other examples of molecules that are formed via radical polymerization. Well, I guess let's start with ethylene, which would form polyethylene. So ethylene is basically just this with, again, remember, hydrogen, 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 hydrogen. And when it polymerizes, it forms this carbon backbone. And I haven't drawn them here, but again, remember, all of these other unoccupied things, or all of these other ones, are secretly the hydrogens that I haven't drawn in here. If you remember back to my earlier lecture on polymers, I mentioned there was another type of polymer called polypropylene. So propylene makes polypropylene when it's polymerized. And propylene actually looks very similar to polyethylene. There's this carbon-carbon double bond, except, one of the carbons has two hydrogens on it. One of the carbons has one hydrogen, but then there's a methyl group, right? A CH3 sticking on this. It turns out that propylene polymerizes in almost the exact same way as ethylene, right? There's basically, instead of an ethylene molecule encountering this radical, a propylene molecule would encounter this radical. And for polyethylene, all of the hydrogens were sort of just carried along for the ride, right? These hydrogens out here didn't really participate in this reaction forming at all. It turns out it's basically the same with polypropylene. The hydrogens are all along for the ride, as well as this carbon that's in the methyl group. So if you imagine, right, there's basically like, if I just pretended that this methyl group wasn't there, then there would be, there would be this carbon-carbon single bonded chain that's made up of these carbons. But half of the carbons, right, half of the carbons have two hydrogens on them, and half of the carbons have another carbon, a methyl group attached to them. So we get this, right? Half of the carbons have a methyl group, the other half of the carbons just have two hydrogens. So in a sense, what does this look like? These carbons are these ones that ended up down here. These carbons right here are the ones that end up right here. And these carbons up here are the ones that end up as these methyl groups right here. So in the same way that the hydrogens just come along for the ride for ethylene, the methyl groups come along for the ride in polypropylene. And basically the same thing happens for polystyrene as well. Where instead of having a methyl group right here, you have a benzene ring. So this polymerizes to form this carbon-carbon backbone, but then there's a bunch of benzene rings on half of the carbons had a benzene ring to start out, half of the carbons in the final chain end up having a benzene ring. In the final result, and you can sort of map, there's sort of a similar mapping. Whatever carbon was this one, is the one that has the side group after polymerization, whereas the carbon here is the one that didn't end up with all that. It turns out that there's basically you can sort of follow an analogous process. It's not, polyethylene, polypropylene, polystyrene, these all form these molecules here. Take a moment now and sketch what this molecule would look like. So the monomer is basically, it looks like ethylene, except it has a chlorine here instead of a hydrogen. Well, what does this look like? It's basically, you know, it's sort of the same thing as what's going on for all of these. Forms a backbone that looks like this. Only half of the carbons, these carbons originally, basically would have a chlorine group sticking off the side, and the other half of the carbons don't. And of course, anything, you know, again, all these carbons are forming, you know, all these carbons have 4 bonds to them. So, you know, the ones that have chlorine also have hydrogen sticking off. The ones that don't have chlorine each have 2 hydrogens sticking off. But again, for clarity, you know, I'm going to follow the organic chemistry notation to sort of neglect these extra hydrogens that stick off. Take a moment now and sketch what you think this polymer or this monomer would look like when you polymerized it. All right, so this one is called poly, well, when it's polymerized, it's poly, but it's vinyl difluoride. So half the carbons have 2 fluorines and half the carbons just have 2 hydrogens. So it looks like this. Half the carbons have 2 fluorines. And I've omitted the hydrogens that are on, right, again, I've omitted the hydrogens that are on the alternating. That are on the alternating ones. This one, I guess. Hydrogen. Take a moment now and sketch what you think this one looks like. So, well, this almost essentially looks the same as polyethylene, except every single hydrogen has, or sorry, every single hydrogen has been replaced with fluorine. And this has a special name of polytetrafluoroethylene. Or it might be called PTFE, or you might know it by its more common brand name, Teflon. So Teflon is this molecule right here, and that makes this right here. So basically, you know, so what's the key thing here? Radical polymerization. All of these basically have these carbon-carbon double bonds. The carbon might have some other junk on the sides, and basically those just kind of those side things don't really participate in the reaction at all. They end up just being side groups on the actual chains right here. So that's radical polymerization. Let's now talk about ring opening polymerization. So ring opening polymerization basically has the monomers start in a ring shape. So monomers start in a ring. So one example of a ring opening polymer is this one. And if I were to sort of fill in, you know, the molecules, it's a carbon, carbon, oxygen, and each of these carbons has 2 hydrogens coming off. And if you imagine, like, you know, this involves a pretty high, pretty substantial strain in the bonds right here. And basically what happens is there's basically some growing ring, so a growing chain, cracks open a ring, and it gets added to chain, and then that then catalyzes the next ring, ring to open. And basically everything that was within the ring sort of becomes part of the chain. So everything joins the chain. So a way to sort of visualize what's happening with this is, imagine I had some process. So imagine each of these things are my monomers. Imagine I had some way to basically start that chain growing. I've essentially opened up something, that could hypothetically reclose with itself, but instead of reclosing it with itself, it cracks open the next ring, and then this next ring has part of that ring that wants to join this right here, but then part of a molecular motif that was sort of analogous to the part that was cracked open earlier, that this one can then crack open the next ring. And again, these are snaps, right? There's like the sort of sticky outy part and the go-in-y part. That cracks open the next thing that can then join the chain. And then you could imagine if I had more and more of these monomers, I could just keep doing that process where I crack open the ring joins the chain, the exposed end then cracks open the next ring. And for example, this molecule right here, if you imagine just sort of opening up this ring and then adding a whole bunch of those open rings to one another, this molecule basically ends up creating something that looks like this. Where the oxygens become part of the ring. Those two carbons are basically in between the oxygen from the next ring and the oxygen that was originally part of their own ring. So basically what was this, or what was this now sort of becomes this, where there are two carbons, there's an oxygen, and it maps that way. So that's what we have here. So now let's talk about how chains form and grow, and we'll talk about step growth versus chain growth. So chain growth, there's basically an active end, and that sort of attacks a monomer that then joins, and what was part of the monomer now becomes, it sort of regenerates a new active end. And then you can imagine this sort of goes back to the start, and you repeat. So take a moment now. Which of these polymerization methods would you say or is best described by chain growth? Well, it actually two of them, radical polymerization and ring opening polymerization, right? So remember, radical polymerization, the radical attacked a monomer, and that created a new radical at the end. For ring opening, the chain attacked the ring, and then the chain sort of had a new end that could attack the next ring. So this is so examples of polymers that grow via chain growth are radical and ring opening. Let's now contrast the step growth, where it's basically any open end of a chain or monomer could join any other open end of any chain or monomer. And spoiler alert, radical and ring opening were chain growth. By process of elimination, you would conclude that that condensation polymers grow via step growth. So what might that look like? Well, if you imagine I have a whole bunch of Legos here, during step growth, these two could join up with one another. These two could join up with one another. A monomer could join this one. These two could join one another. a different one could join here. So it's not like radical where there's like only one unpaired electron where monomers keep on getting added to the end. Step growth is a free-for-all in that anyone can join with anyone, and then eventually we all end up as one big happy family. So, thus concludes our qualitative description of polymer synthesis in the 3 types of polymerization reactions that form and the 2 distinct ways that chains grow and how they correspond to it. So thank you very much for watching, and good luck with your study of biomaterials.